And it's recording. Okay, hello. Okay, so for this tutorial, we'll just go over some things about Shapley values. Okay, so we've been talking about cooperative games. We started talking about cooperative games, and the first thing we talked about is the Shapley values, and those is basically dealing with how to fairly distribute the value of a of the coalition into the individual members. Okay, so I'll just briefly review what Shapley values are, and I'll do I guess I'll do a hard example from last year's questions, and then we'll see what we can do after that. Okay, all right. So Shapley values. So so the idea of Shapley values is, so it is a way of fairly distributing the value of a coalition using each player's marginal contribution. Okay, so the way that cooperative games work is that each subset of players is a coalition and they generate some value. And if we have a particular coalition that generated that particular value, we want to know how we can distribute that to distribute that value to the individual players in a sense, in a way that is fair. Okay. Right. And the way we do that is through marginal contributions. And that is we look at what happens to the value of a coalition when the player is in or out. Okay, so so the official definition, it's a long one. So official definition. So for a, so if you look at, we're looking at the permutations. Right, so we're looking at this being a permutation of the players and right, and the marginal contribution of one player of a player I is right, the value of the coalition consisting of I and everything before it, everyone before, or minus the contribution, minus the value of the coalition. Of just only the everyone before it. Okay. So if we imagine that this is a permutation of the players, here's player I, we're looking at the value of this coalition. This is this is the one that is in positive, minus the value of this coalition. Right. So this part, this coalition minus the value of this coalition. So this gives you the actual contribution of player I to the coalition in front of it. Right? So adding I gives you this much more, and that is the marginal contribution. Okay. All right. And the Shapley value, oh, it's wrong color. All right. So the Shapley value is basically you sum over all the permutations of the marginal contribution and average it out. Right? So the Shapley value is the average marginal contribution of a player over all permutations. Okay. All right. Okay. All right. Okay. So the official definition, in symbols, this is the average. So there are n factorial permutations. The average is that. You sum over all the permutations. Okay. And you're looking at the marginal contribution of player I in that permutation. All right, so that is the Shapley values. Right? So you take all the permutations, you look at the marginal contribution, and you look at how much player I contributes to that in that particular permutation, sum over everything, and then divide by n factorial. Okay. Right. And the reason why we say this is fair, this is a fair distribution of the values, is because it satisfies the four nice properties. Right? So you have the efficiency, dummy player, symmetric, and the additivity. Okay, so the, the fairness is comes from the four properties. Right? So efficient, meaning it does distribute everything, all the values to the players. There's a dummy player. If a player does not contribute to any if it doesn't contribute to anything, then it will get 0. There's symmetric. If two players equally contributes to the same things, then they should get the same Shapley value. And the strange thing is additivity, which is if you take two games, add them together, the Shapley values will also add together. This one is not as obvious why this is important, but the important thing is that Shapley values is the only function that satisfies all four of these good properties when distributing the values of a coalition. All right, so that's the basics of Shapley values. Okay. All right, so let's see if we can do a problem with Shapley values. Okay, so this is going to be a little bit harder. Okay, so here's a problem. We're going to have a cooperative game such as NV. Okay, the players and the values of the coalitions. Okay, and we're going to have a particular subset of the players, T. Okay, we will assume that T is at least 1. And so we have a we have a cooperative game, we have n players, and we have a special subset of players inside this. Okay. And what we want to do is we want to change the game slightly, right? So we're going to change the game so that if my coalition, if my subset contains this special group of players, we're going to add values to it. Okay, we're going to add value to its coalition. Right, so any coalition that contains T, right, we're going to add the value of alpha. Okay, so I suppose we raise the value of any coalition containing T by alpha. How would the Shapley value change? Right, so you have the original game and you have a Shapley value for that game. And all of a sudden, for any coalition that contains this particular subset T, we added some value to that coalition, right? So everything will be increased by alpha if it contains T. So now the question is, how would you calculate, how would the Shapley value change in this case? Okay, all right. All right, we can think of this, for example, if T is just one player, right? So if T is just one player, then anytime you have that player, the value goes up by alpha. Right? So then naturally you would think then that the Shapley value of that player will go up by alpha as well, because it will just contribute alpha more each time it's in. Okay. And nothing else changes, that nobody else has any different Shapley values. Right? So that's what we would think if there is only one player in this. Okay. Okay. But what if there are several players? Maybe there are 5 players in this set T. And anytime those 5 players are in a particular coalition, the value goes up by alpha. Okay. So how would the Shapley value change in that case? Okay. All right. Okay, so what we will do here is let's formally write down the new game, right? So we define n v prime by v prime of s is, let's say this is v of s plus alpha if t is a subset of s and it doesn't change otherwise. Okay, so it doesn't change otherwise. Okay. All right. And for the notation purposes, I'm going to let phi and phi prime be the Shapley values of NV and V prime, respectively. Okay. And we want to write phi prime in terms of phi. Okay. All right. So that's the problem, right? So you have a cooperative game, just any cooperative game, and anytime, and then we change the cooperative game in the sense that anytime you have a coalition that contains my set of special players T, then the values go up by alpha. Okay. And we want to say, how do we write the new Shapley values in terms of the old Shapley values? Okay. All right. Is that okay? Is the definition of the problem okay for you? Okay. All right. So if we want to look at the Shapley values for the new game, then we will look at the definition of Shapley values and look at the marginal contributions of a player in the new game. Okay, and we will try to relate that to the old game. Okay, all right. So for a new game, right, so we look at the marginal contribution of a player in the new game relative to the old game. Yeah, old one. Okay, there you go. So we're looking at the marginal contribution of a player in the new game relative to the old one. Okay. All right. Okay, and we'll have two cases. Right? So we'll have two cases, right? The first case is fairly simple, right? So we will look at the case when my player is not in T, right? So in the first case, I is not in T. So suppose I is not in T. Okay. All right. And we have a permutation, sigma with I somewhere in there. Okay. And we're looking for the this minus this, right? So we're looking at the value of this minus the value of this. Oops, that's the wrong thing. Right, so we're looking for the value of that. Value of everything before I plus I, including I, minus the value of anything before I. Okay. All right. So the idea here is that I is, well, not in T. So the difference should not really change, right? So we either have, either all of T are in front of I or not. Or not all of T are in front of I. Okay. All right. Okay. All right. So if T is entirely inside here, right? So if T is entirely inside here, what does that mean about the values of these two collisions? Okay. Right? If T is entirely inside here, then the value of this collision will increase by alpha, right? Because T is inside here. And also the value of this collision will also increase by alpha, right? So if T is in front of S, in front of I, both collisions increase by alpha because they do contain the T. Okay, right. So if T is in front of I, all of T is in front of I, then both of these coefficients will increase by alpha. So that is great. The difference is, so this is the marginal contribution is the same as before. Okay. Okay. But what if T is not totally in front of I? So there could be some T here, some T here, some players in T here, and some players in T there, or it could be all the T is in after I. Okay. Right. Hopefully you can see that this means that it doesn't change either, right? So there's no change to this value and no change to this value because T is not in there, right? So if not, then values do not change. Okay. All right, so in either case, it is basically the marginal contribution is the same either way, right? So in both cases, the marginal contribution, let's just say marginal contribution. This is just the marginal contribution of the player I from before. Okay. So marginal contributions are all the same. So you can just say for player I, the Shapley values do not change. Okay, so that is the easier case. I'm missing some details here in terms of actually writing out what the formulas are for this one and for this one, etc. But we'll leave that detail to you. Okay. All right. Okay, all right. So that is the case when player I is not in my special set T, set of players T. So their contribution does not change. Their marginal contribution does not change. So their Shapley values do not change either. All right. Any questions so far? Okay. The more interesting case is when player I is actually in T. So the player I is actually in T. Okay. Right. So player I is in T. We look at this situation again. Right? So we're looking for the value of this coalition, including I, minus the value of this coalition, not including I. Okay. Now, in a lot of the cases, the marginal contribution would be the same. Right? So if you have some parts of T here, some parts of T there, or all of the remaining T's are in there, then nothing changes. Okay. All right. So the only thing that changes if is so for most cases, the marginal contribution does not change. Okay, so for most cases, the marginal contribution does not change. Okay. Okay. But what it does change is when all the rest of T are in front of I, right? If the rest of T is in front of I, right, so the T consists of I plus something else. If the rest of T are all in front of I, then this coalition without the I is the same as before. Don't change the value. But now this coalition, which now contains T, now it does have a added alpha to it. Okay. So in the case where the remaining, all the remaining players in T are in front of I, now we do have a change in value, a change in marginal contribution. Right. So the only case where it changes is when T minus I are all in front of I. Okay, so they are in front of I. Okay. Okay. Okay, so the only case is when it changes is when T minus I are all in front of I, right? In this case, the marginal contribution of I here is going to be the original marginal contribution plus alpha, right? Because the top part here has alpha added, and this bottom part here is not added. Right, so that is the marginal contribution is increased by alpha. Okay. All right. Hopefully that makes sense. Any questions so far? All right. Okay, so now what we have is a counting problem now. Okay, because the marginal contribution increased by alpha for permutations where everything that's not everything is in T except for I is in front of T, in front of I. Right? So if you look at the value, the Shapley value formula here, right? So if you look at this Shapley value formula, we see that this contribution So we see that this contribution increases by alpha for certain permutations. Okay. So the total increase would be alpha times the number of permutations for which it increases. Right? So you just look at the sum, it increased by alpha for some permutations. So then the overall thing would just be, so this sum will increase by alpha times the number of permutations with this situation. Okay. All right, so now, so we need to count the number of such permutations. And Shapley value increases by, there's a 1 over n factorial at the very beginning. Okay. And it multiplied plus alpha times, I guess, that number. Oh, what is that number? Let's call it m. Number m of such permutations. So this phi I would phi I, yes. So I guess the Shapley value will increase by this much, right? Because if you look at the formula again, for the formula, the delta, the marginal contribution, increased by alpha for some permutations. So we look at, so this sum increases by alpha times the number of such things, and then we divide by n factorial. All right. Okay, so now we just have to count. Counting is fun. Okay, so this is where you need to go back to your counting skills and see where how you can count this. Okay. All right. Okay. Okay, so let's see, how do we do this? So how do we count this? Okay. All right. Okay, so we have I somewhere in here, and we have t minus 1 elements somewhere in front of it. Okay, and everything else has to be arranged in some way. Okay. All right. Okay. All right. So this is where we are going to get, I guess we'll do some very tricky counting here. Okay. All right. So the first thing we're going to do is let's pick where all the t, where the elements of t are in this permutation. We'll first pick the spots where elements, players in T occupy in this permutation. Okay, so let's first pick the spots. Okay, so maybe it will go in here, 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 for example. Okay, so let's pick the spots where the players in T will occupy this permutation. Okay, and the number of ways to do that is n choose size of T. So n choose size of T ways. Okay. All right. All right. So once we pick this, pick the spots where the for all the T's will go in, we need to say, where does I go? Well, I has to go in the rightmost spot, right? So player I goes into the rightmost spot. Okay, so player I goes to the rightmost spot there. Okay. All right. Okay. Now that I goes into the rightmost spot, we will fill in the rest of the permutation. Okay, so we'll fill in the rest of the permutation. So for these spots that are supposed to be reserved for T, right? There are T minus one of them. So if we want to put the players in T, except for I, into this, there are T minus one factorial ways of doing so. Right? So there are T minus one factorial ways to fill in T, fill in the spots for T. Okay. Right. So there are T minus one spots like this, and T minus one things to fill it in, right? So there are T minus one factorial ways of filling those spots. Okay. But we also have the other spots like this one, these ones, right? So these spots has to be filled in with the rest of T, right? So there are n minus T of those, right? So the remaining n minus T elements can fill the n minus T spots in, not surprisingly, n minus T factorial ways. That factorial does not look factorially. So here. All right. So once we fill out the spots for T, you just fill out the rest of the spots. There are n minus T of them. Okay. All right. So our value m, the number of permutations where I is basically the last one in T, right? This one is going to be n choose T times T minus 1 factorial times n minus T factorial. Okay. All right. Okay, so this is where a little bit of combinatorics from before might help. All right, so n choose T is n factorial times T factorial n minus T factorial. Yeah. Okay, and we still do T minus 1 factorial n minus T factorial. Okay. And these two cancel out. And the T minus 1 factorial and T factorial ended up just being 1 over T. Right, so this is actually n factorial over size of T. Okay. So n factorial over size of T. All right. All right, so if you look at this formula here again, right? So m is represented by n factorial over t, right? And the n factorial will cancel out with each other. So that means that alpha I increases by alpha over size of t. And that is our answer here. Okay. Okay. So this is our answer. If you have any coalition that includes t, I increase by alpha, that means that the Shapley value will increase by alpha over the size of t for every player that is in T. Okay. And that makes sense, right? So that makes sense, right? Because as a group, these T players will add alpha each time they're in a coalition. So naturally, you would divide the bonus of alpha evenly among these players here. All right. All right. So all the players in T, their Shapley value increases by a portion, the 1 over T of the increase alpha. All right. All right. So that is that example. I did skip like details, like these are not really formal. So if you really want to write it out, you probably need something more formal. But hopefully you understand the idea behind this. Okay. All right, good. Okay. Any questions? Okay. All right. So I've looked into Shapley values, and apparently when I search for Shapley values, the concept of machine learning comes up quite a bit. So I will do a idiot's guide to Shapley value for machine learning. And when I say idiot's guide, that means I'm the idiot. I don't know much about machine learning. I just learned it in 1 hour of what Shapley value has to do with machine learning. And I'll just give you a very brief idea of how this is being used in machine learning. All right. So the way I imagine machine learning is that you have a bunch of data. You have a bunch of data that you want to make decisions on, right? So it could be, for example, you have a bunch of data on a house, various properties on the house, and you will say that house is worth this much. Right? So those are some data, and you feed this into a black box. This is where the machine learning. So this is where the machine learning takes place. They will take the data and magically learn something about the data. Okay. Okay. And once they have learned this, they will say, well, here's another new data. Tell me what you predict it should be. Right? So I have a bunch of data, for example, the housing situation, for example, feed into this black box so that the machine can learn things. And then I give you another house, another house with new data. And then the black box will use the data they have been trained with to predict what the actual price for this new house would be. Okay. And that is a very primitive description of machine learning. If you actually know machine learning, you can laugh at me. It's okay. All right. Okay. All right. So the problem with machine learning, though, is that this process is kind of an unknown, right? So it might be using neural networks, any sort of stuff like that. And those are the things that you can't explain, right? So the predictions can't be explained by the black box. Right? So you feed in some new data and it predicts feeding a new data for a new house. It predicts that house should be worth this much money, but they cannot tell you why they say it is this. Okay, right? So they cannot explain why that is. Okay? And sometimes this is quite important, right? So sometimes this could be crucial, right? So for example, if you're using the machine to decide whether somebody gets a loan or if somebody gets a job based on their resume, then the machine will say, well, you are accepted, you're rejected, but they cannot tell you why you're accepted or why you're rejected. Okay. All right. All right. So from what I read, this is where Shapley values can come into play in terms of trying to explain why something happens, right? So Shapley values may be able to explain some of this. Okay. Okay. All right. And the idea is that the data has several entries, right? So several features, or what they call features, right? So these are different categories of data, right? So it could be for a house, it could be number of stories, it could be how it's made, when it's made, what neighbor it's in, etc., etc. So those are the features of the data. Okay. All right. So what one could do, based on based on a short reading, is that you can calculate the influence of each feature on the prediction by calculating its Shapley values. Okay, so this comes into play because it calculates the contribution, okay, to the prediction. Okay, so you imagine a cooperative game where you only use some of these features, and that will make a prediction. Okay, and maybe you'll take some features out and then try to make a prediction, and then use that to calculate Shapley values. And in that case, that will tell you how much of an influence it has on the actual prediction. And that might give you some idea, I say might with a very big quotation mark, might give you some ideas of how each feature will affect the prediction. For example, for a house, maybe the main factor for a house could be, the age of the house. Maybe how much does it influence the prediction of the prices for the house? Or if you have, say, what's the size of the house, that definitely influences the prediction quite a bit. Okay, so we can use Shapley values to kind of say how much does each of these features will affect the prediction by our black box, because the black box by itself doesn't know how they decide what would be the outcome of our data. Okay, so that is an idiot's guide to Shapley values for machine learning. Okay, I don't know if that's it's interesting or not. And if you're in machine learning, you can probably look into this. There is a lot of paper on this online as well. All right. Okay. Well, we're also almost out of time. Any questions?
No, thank you, Professor.
Okay, no problem. All right, so thank you very much for coming. And next week you'll have the next quiz, so be prepared for that. I won't see you in the quiz, but hopefully you can do well in the quiz. So yeah, all right, so thank you for coming, and I hope you have a very good day.
Thank you. Thank you.